Okay, so in this short video, I'll talk about this paper by Feynman in 85 titled Quantum Mechanical Computers. So I'll try to do this over course of many weeks or months depending on my schedule. So what I want to do in this part is to introduce some basic stuff regarding classical logic gates and then talk about reversible ZOR and CC0 gates. I'll explain what those are. So let us first start with what we know about classical computing. So classical computing is based on a two-state idea. That is, we have either 0 or 1. So let's say we have this AND gate, which we show here. So A and B can be inputs, which can be 0 or 1. And then based on the inputs, we have an output of the AND gate, which is given by this. So this is always 0 except when both the inputs are 1. So that is this case. So this is known as the logic table and this is the AND gate. So similarly, there's another gate which we call OR gate, and the logic table for OR gate is something like this. So it is 0 only when both the inputs are equal to 0. If any one of the inputs are 1, then the output is 1. And OR gate is represented by this diagram. So there's this curve here, and then these are the input and this is the output. Now if we consider the output, which is the complement of the AND gate, which was shown before, and OR gate, which is shown here, we obtain what are called NAND and NOR gates. So this is a NAND gate and this is a NOR gate. So for NAND gate, I just take the AND gate and put a small blob at the front, and this is known as NAND gate. And if I take the OR gate and put a blob at the front, it becomes NOR gate. So the logic table for NAND and NOR are like AND or OR, except that we take the complement of the output. So for example, a NOR gate will always be low, except when both the inputs are low. So if both the inputs are low, then the output will be high in case of NOR gate. So it is completely opposite outputs for the corresponding AND or OR gates. NAND and NOR are also known as universal logic gates because you can construct any classical circuit using these gates. The next important gate which we consider is known as ZOR gate. It is also known as exclusive OR gate. So what is the truth table of ZOR gate? The truth table of ZOR gate is that if both the inputs are the same, then the output is 0. If both the inputs are different, then the output is 1. So if it is 0, 0, then the output is 0. If it is 1, 1, then the output is 0. In both other cases, it is 1. So how do we represent the ZOR gate? We represent the ZOR gate like this. We take the OR gate and then put a small arc in front of the input, and this is the ZOR gate. One important thing about ZOR gate is that we can also consider what is called a reversible ZOR gate. So what is a reversible ZOR gate? The reversible ZOR gate is a ZOR gate where you have another input apart from the two inputs, which is known as A prime here, and then you have an output which is B prime. So we take the usual A, B and then add A prime, B prime to get something like this. Now this is important because we see that A prime is always same as A. So if A is 0, A prime is 0, and similarly for 1. This A prime is also known as control line. We'll understand what this is later on. This is known as control line, and this is also known as garbage output sometimes. In Feynman's paper, it is also referred to as garbage output. So what exactly is this? It says that if you have 0, 0, 0, then you have 0, and if you have 1, 1, 1, you have 0. In both other cases, it is equal to 1. It is easy to convince ourselves that this is reversible. This is reversible because if I take 0 0, I get 0 0. If I take 0 1, I get 0 1. So these are the same pair. If I take 1 0, I get 1 1. And here, if I take 1 0 as input, I get 1 1 as output. So this input, it gives this output, and this input gives this output, and we see that they are the same. So in some sense, this is reversible, right? So you can either read it from this way or this way. It is the same, so it is reversible. We now mention an important detail about this reversible Zorgate. We can directly consider the quantum analog of a reversible Zorgate, which is known as C-NOT gate or controlled NOT gate, and that is what we'll now talk about. So what is a controlled NOT gate? Before talking about control NOT gate, let's just show the matrix representation of C NOT gate, which is given by this. So there is 1 0 0 0 and there is 0 1 0 0, and the third and the fourth rows have them swapped. So you would have ideally thought that one will be here and one will be here, but it's not the case. It's opposite. So this is the representation of control NOT. So we'll come to other quantum gates later on, but what is control NOT quantum gate? It transforms the quantum state, which is given by this, into a quantum state which is given by this, and it is completely a quantum version of what we have shown here for the reversible Zorgate. So what we get is there is the input A and B, and then there's this control line which we discussed before. This is A prime, and then this is B prime. So it's exactly the same notation as here, and this is known as control line, so it is exactly the same. And then this X is the Feynman notation, and modern notation is something like this. So what happens is you have these inputs, and this goes through, and this is flipped based on what this B is. So if we look at Feynman's article, this is the article which I was talking about. So this is the article in which he discusses about the possibility that the classical computers can be updated by quantum computers to simulate many important physical theories. So he mentions about the fact that quantum physics laws are reversible in nature. So we have to consider quantum computing machines which also obey such laws. And he discusses the fact that in computer science, any universal computer can be made by suitably connecting primitive elements, just like these gates we are talking about. So he also mentions in this these lines here about the controlled NOT gate, which we just discussed, and this yeah, so this is exactly what we talked about, that they are the same. A and A prime is always the same. The A prime is always the same as A, which is known as the control line. If the control is activated at A is equal to N, then the output B prime is not of B. That is, it's just opposite of B. So if the control line is high, then what you have B, it is flipped. Otherwise, it is not flipped. Okay, so now if we have control NOT, there is something also known as CC NOT, which is controlled control NOT. This is also known as Toffioli gate. This is a universal reversible logic gate, and any reversible quantum circuit can be constructed out of these. So let's look at the logic table. We are familiar that the diagram will look something like this, because this is the control line, and again this is the NOT gate. So this is like C, this is C, and this is NOT. So that's why it's CC NOT, and this is the modern notation. Let's see the truth table or the logic table for this case. If so, for the ones which are mentioned by the blue arrows here, A, B, C is the same as A prime, B prime, C prime. So you can check that all these cases, A prime, B prime, C prime is equal to A, B, and C respectively. But what happens when A and B are both high? If A and B are both high, then C is flipped. So for example, if A and B are high, like in these two cases, C is flipped. That means C prime will be opposite of C. So that is why you get 1 1 1 here and 1 1 0. And this is CC NOT gate. The matrix representation of CC NOT gate, you can convince yourself, goes something like this. as we can see, there are diagonals on one here, except the last two parts, which is corresponding to these two parts, where it is flipped. And this is known as CC not gate. So Feynman, in his article on page 2 of that article which I just discusses not gate, which we discussed, and gate, and he also talks about controlled not, where the logic table is given by this, and controlled CC not, where the table is given by what we just saw. This is just table 1 in Feynman's paper, which is mentioned here. So what happens to control not? Let me just again re-emphasize. If A and B are 0 0, it's the same. 0 1, it's the same. If A is high, if A is equal to 1, then B is reversed. So 1 0 becomes 1 1, and 1 1 becomes 1 0. So this is what I wanted to discuss in part 1 of this video. In the next video, we will discuss other quantum logic gates like Hadamard gate, Pauli gates, and many other gates, and then we'll eventually go to discuss and construct quantum circuits. So thank you for listening.